All class, I'm going to be going over case study 1, machine guarding and start interlock. My name is Luis Rivera, and in this short video, I'm going to be walking over how to build and analyze a Boolean model for a machine guarding start interlock system, with the focus being in not getting the right answer, but rather than showing the thought process to get that correct answer. So the first step of the assignment looks to define the Boolean variables, particularly the inputs and outputs. I'm going to go over what true and false means for each of the specific physical conditions. Okay, I define guard door closed with a G, emergency stop not pressed with an E, operator start command given with an O, and temperature parameter that details whether we have an overtemp fault present. Going over G, true means that the guard is fully closed, while false means that the guard is open. Regarding parameter E, true entails the E stop is okay, while false means the E stop is pressed. In regards to the O, true communicates that the operator pressed obviously start, and false mean that there is no obvious start request from the operator. And in regards to T, a true entails fault condition, while false entails normal operation. Outputs would be S as in motor alarm to start, and A as in alarm active. And the way that these parameters are defined, it is implicit that S true entails that we have a start condition, and as false entails that we have a no start condition. And regarding the alarm active, the nominal state is true, meaning we do have an active request, and false would entail that we do not have an active request being sent out. The next step of the assignment would be building the actual Boolean rules. I'm going to be creating 3 simple logic rules describing how this particular system behaves. I'll say them in words and also show the Boolean expressions. Going into rule 1, motor can only start when all safe conditions are met. This implicitly is constructed by guard closed and emergency stop okay, and inverts no over temperature fault, and operator request start, as detailed by this statement. Regarding rule 2, alarm activates if any of the critical safety conditions are violated. This includes guard open, emergency stop pressed, or over temperature fault. So that gives us parameter A as an alarm active. This is going to be an inverse of G, being guard closed, an OR gate with an inverse to E, emergency stop not pressed, with a final condition of an OR with over temperature fault present with the T. Going into the third request for the rule, a start request while unsafe should never allow the motor to start in this particular system. This really is a constraint from rule 1, but if we were to state it directly, it would be that if operator start command is set to true and any of G or E or T, so G is guard closed, or E emergency stop not pressed, or T over temperature fault present, are unsafe, then S must be false, as in motor alert to start. So this is a safety condition that we want to have hardwired into our control via this fault monitor. Going into the partial truth table, particularly under model analysis, you're going to have case 1 being all safe and operator presses start. This is going to give us a guard door closed to true, emergency stop not pressed to true, operator start command given to true, and finally no overtemp condition. As a result, this is going to give us start command to 1, with an AND gate to 1, AND gate to 1, and this is going to give us ultimately a 1, given that we have all true conditions for the start. In regards to alarm active, which is this condition here, we have alarm active. It is set to false with an OR gate to 0 with an OR gate to 0. So all conditions in this logic path get us to 0. So essentially the machine starts and no alarm is active. That is normal operation, so this matches our expectations. Going over case 2, we have a guard door closed, meaning it's open, given this is a false. We have emergency stop not pressed, so it is pressed, given it's a 1, and O being set to 1, which is that the operator press start, and finally the T condition here on case 2, 0. So overfall condition not present is what this one entails. As a result, start is going to get us a no start request, and a alarm active here would get true in conjunction with an OR gate with a 0 with an OR gate to 0 is going to give us ultimately, given the OR gate characteristics, if we have a true boolean, it is going to pass through. So we have that true boolean here. The system effect of this conclusion is we could say that the motor is blocked and the alarm is active. Again, this behavior is what we would want the control to dictate in this particular condition. A blocked motor while we have an operator requesting a start. The assignment then goes into a simplification example. I chose the alarm rule. The alarm condition equals to a not an inverse of a guard door closed. So we have an open guard door with an OR gate with an inverse to not E. So emergency stop not press. So if it's an inverse, that would detail that we did press that emergency stop. And finally with an OR gate to over temp fault present. What this entails in simplification form is this is already a minimal or sum form. So it basically communicates that each term represents an independent safety failure. As a result, there's no further redundancy to act on, and this erases the value that each term is necessary for this condition. After the simplification example request, the assignment calls for a safe operating condition. Now, from rule 1, we know the system is guaranteed safe for motor startup only when we have a guard door closed, emergency stop is okay, and temperature is normal, and the operator requests a start. This gives us a clear Boolean safety envelope. Now, in last thoughts, I would like to first go over the interpretation and finally a closing statement. Going into the question of what did this Boolean model help me understand, I would say it helps me break safety logic into simple testable statements. I can quickly see how the system reacts to faults and how different conditions interact. As an engineer, knowing how to do this, I would say strengthens my ability to design, troubleshoot particularly, and validate that the control systems systematically meet the intentions or the expectations instead of relying on intuition. Basically data-driven decision making. One limitation of the true and false approach, I would say, is that the real systems often have nuances, right? We have sensor delays. We have, for whatever reason it may be, where it's hardware driven, where it's connection related. We can have also partial failures, analog values, or timing requirements that are very, very quick in nature, a very fast response. So data capture of this and being able to assess whether those triggers are all tactically being scheduled is definitely a challenge. Additionally, we have uh, fuzzy logic, we have parallel threading, we have asynchronous processing. So all of these are different protocols that meet various needs, and as a result, not everything can be modeled through only Boolean logic. However, Boolean logic does capture the structure of a decision process, but not the particular timing uh, or probability. It's useful for abstraction, but it cannot represent everything. Um, if I were to look at the value of how this makes me a better engineer as a final statement, I would say that the Boolean modeling process definitely helps build clarity in our engineering practices, and definitely makes a better environment where we are able to develop safe, logical, and reliable systems through data oversight, confirming whether we are in the right step or whether a redesign or revision is warranted. Thank you, class.